over the weekend, you should have watched, I believe it was a 10-minute and 39-second video of expanding and condensing and changing of bases. Okay, I'm fully aware that some of you didn't watch it. Okay, it's not a surprise to me. When we put it out there, we said that we probably are going to have maybe 25% people watch the video. I get it. Okay, all right. So if you're in that 25%, kudos to you. Okay, if you're not in that 25%, it's still out there for you to watch if you're confused by the stuff that we're doing today. Okay, because we need to do that stuff in order to get to where we want to get to today and tomorrow with solving exponentials. Okay, so there are three properties out there that we are using very much so. Okay, and those three properties are the product property, which if you are multiplying two things, you split them up, you expand them into two logs with addition. The quotient property, if we're dividing two things in a log, we can expand that out and divide them, or subtract them, I should say. And the power property, which says that I have a power in the argument that can go out in front and become a coefficient on the log. Okay? So, with that being said, this one, if I am expanding, that means I'm going to have to be writing multiple logs here. So this would become, because it's a quotient in here, it's a dividing type of a problem. That means I'm going to take the natural log of x squared minus the natural log of y cubed. Or if this were a log with a base problem, then I would have these, instead of being natural logs, those would be logs with the exact same base as what I started in. Okay? All right? So I've expanded out using my quotient and my product properties. Okay? I do that first when I am expanding, and then I apply the power property. So this 2 right here and this 3 right here are exponents in the argument. They can come down in front, and that is the expansion of mine. Okay? Now, the reason that we expand them is because sometimes we might be able to change one of them. So, for instance, if I had log base 3 of 9x, okay, multiplication, so that's going to become log base 3 of 9 plus log base 3 of x on the expansion. Okay? And now I can't necessarily do anything with log base 3 of x because I don't know what x is, but this log base 3 of 9, whenever I've got a log and I've got a number in there, I'm always thinking, what exponent can I put on my base that gives me that argument? So here I'm looking at what exponent can I put on 3 to get 9, and that is 2. So this is 2 plus log base 3 of x. Okay? And then if we were in the solving problem, now we could subtract 2 from both sides and go on with that. Okay? So that is why we do it that way. Okay? Condensing is working in reverse. Okay? So first thing you're going to do is you are going to apply the power property when you are condensing. Okay? So you apply the power property first. Then you apply your product and your quotient properties left to right. Take 2 at a time. Okay? Don't try and get confused by trying to do multiple ones. Make it easy on yourself. Take 2 at a time. So this would become the natural log of 2 divided by x minus the natural log of y cubed. I took the first 2 and condensed it down. Because it's subtraction, it becomes division. Okay? Then I take the next 2, the natural log of 2 divided by x. Then that has to be divided by y cubed. And now I say proper math tells me that I don't really like a fraction in a fraction. I should probably do something different with that. So I would say here, well, this is 2 divided by x divided by y cubed, which is 2 divided by x times 1 over y cubed. So then this would become the natural log of 2 divided by xy cubed. And if you want to put it in parentheses, that's fine, but you don't have to put it in parentheses because it's one single solitary term. Okay? If it were multiple terms, yes, then you would put it in parentheses, or then you would have to put it in parentheses. Yep. So that is what you should have gotten out of the flipped videos. Okay? Solving exponential and logarithmic equation ones. Okay? So I'm a step kind of a guy. Okay? I like to do steps. Okay? The first step in a solving type problem is you need to isolate. So if it's an exponential type problem, isolate. Side note, if you're in the blue packet, flip all the way to the back to the blank side of the last page. That's where you can go. If you're on a separate sheet, be on a separate sheet. That's fine too. But don't put stuff on that for Thursday thing, because we're gonna use those tomorrow. Okay? Alright? So first step, isolate. So if I'm in a logarithmic problem, I'm going to get one single solitary log. I want it on by itself on one side of the equation. If I'm in an exponential, I want one single solitary base with an exponent where the variable is, nothing else. Nothing above it, nothing below it, nothing in front of it, nothing behind it. Okay? I want one single solitary log, or one single solitary exponent. Okay? So, in this particular case, here is my term that I am going to isolate. I'm going to use my order of operations. Addition comes before division. Okay? Subtraction comes before multiplication. All of that fun stuff. Okay? PEMDAS, if you will. Okay? So, in this particular case, I am going to divide both sides by 3. Now, that's going to give me 4 to the x over 2 power equals 32. Okay? Then, what I'm going to do, now that I've isolated my exponential term, or if it was a logarithmic one, I do my logarithmic. Okay? My second step is I am going to change forms. So if it's in exponential form, I put it in logarithmic form. If it's in logarithmic form, I put it in exponential form. On Friday, you wrote down on the front side of your blue packets, you wrote this down. And hopefully, this triggered some synapses in the old brain, okay, where when you've got an exponential, base to an exponent equals argument, that is the same thing as log of that base of the argument equals the exponent. Okay? I will tell you this. The faster you get that out of that long-term memory storage file cabinet that you have in your brain, okay, the faster you get that out of that storage area, okay, easier this stuff will be, because you're going to do this every single problem when you're solving. You switch forms. That's what you do. You switch forms. Okay? So this becomes x over 2 equals log base 4 of 32. Okay? That's what that becomes. Okay? Now, you go through and you solve that one. Okay? Now, if you're not familiar with log base 4 of 32 is, okay, by the way, it's 2.5. Okay? If you didn't know that right off the top of your head, you have one of 3 options at your disposal. You have the change of base formula at your disposal. So you could say that this is the common log of 32 divided by the common log of 4, which again was part of the video on Friday, change of base formula. Okay? Log 32, so log of the argument divided by log of the base is change of base formula. Option number 2, you're not a fan of common logs, so you could go natural log of 32 divided by natural log of 4. Those two will always work. Okay? Change of base form always works. Your other option is, I need to find the exponent that I'm going to put on 4 that's going to equal 32. Okay? Now, luckily, 4 is 2 squared. So the left side is 2 to the 2 triangle power. Okay? Luckily, 32 is 2 to the 5th. So 2 to the triangle power has to equal 5, so my triangle has to be 5/2. Okay? Now, this worked because 4 and 32 were both powers of 2. If this would have been 4, or log base 4 of 36, this doesn't work. Okay? That third method doesn't work. It only works in special cases. Okay? But the change of base formula works in all cases. Okay? So this is x over 2 equals 5/2. So I need to multiply both sides by 2, and I get x equals 5 as my answer. And lastly, what I would do is I would do a quick check just to see if I'm right. Okay? So I'd plug x back into my problem, and I would do that. Okay? So I would say 5 divided by 2 is 2.5, so I do 4 to the 2.5 power, get 32, then multiply that by 3, and I'd get 96. Okay? So quick checks just to make sure. Okay? What I would like you to do now is I would like you to solve this particular example. All right, so first off, I would go through and I would subtract 13. Okay? So then that gives me 3 times 6 to the x power equals 8. Divide both sides then by 3. That's going to give me 6 to the x power equals 8/3. Yes? Okay. Switch forms with that. So then this becomes x equals log base 6 of 8/3. That one I can't do because I can't get it in both base 6's. Okay, so then we're going to go log base 6, or log of 8/3 divided by log of 6, or natural log of 8/3 divided by natural log of 6, and I get here that x is equal to 0.547411. It's putting the 411 in this problem for us. Okay, really it goes on longer than that. 41122893816, but we'll round it there. Questions on that one? Yes, ma'am. We'll tell you if on the test. Yeah. At least 3. Yeah. But then again, if I were using this in the problem further on, I'd leave it in my calculator. You know what I mean? Yeah. Yep. Okay. Try that one, please. So, first step. Okay, so what are we going to do? Going to subtract 8. Oops. Oh, tap the brakes. Just all, yeah, exactly. Yeah, exactly. Guy made one mistake and you jump all over him because your name's on the board.
What? That was talking about myself.
Oh, okay.
I was like, oh, I messed it up.
So negative 5e to the negative x equals 8. Love it so far. Next step. Divide by negative 5. Love it. E to the negative x equals negative 8/5. Love it. Excited. Now what? So now we're going to switch forms with it, right? Because we've got our exponential term isolated. So I switch forms with it. Okay? So this becomes negative x equals the natural log, because it's log base e, right? Loge is a section at Miller Park, okay? The Loge level, okay, at Miller Park. It's not something up here, okay? Natural log is log base e of negative 8/5. Right? Now, one of the things that you should have gotten out of Friday and from logs the last time you did them was that in a logarithmic function, okay, so if I have log with a base of the argument, oops, that's supposed to be a g, okay, of the argument, both of these, the base and the argument, have to be positive. If they're not positive, you're saying, what exponent can I put on a like in this one, okay? E is a positive number, right? 2.7181828926, something like that, okay? You're asking, what exponent can I put on a positive number and get a negative result? Okay? Now, mathematics tells me a positive times a positive times a positive times a positive, however many times, is always going to be positive. Okay? So this is not possible. So there is no solution to this one. Okay. The base has to be positive. The argument has to be positive. Okay. Your exponent can be negative because then we just have reciprocals. Okay. I can have 2 to the negative 3rd power. Okay, that's 1/8. I can have that. Okay, but I can't have 2 to the x power equals negative 8. I can't take a positive number and somehow then make it so that we get a negative answer, or a negative result. Okay, so that's a no solution case. Try this one, please. do a spot check here. First thing, subtract 2. That gives me negative log of 2x plus 1 equals 4. Then what? Divide by negative 1 or multiply by negative 1. Either way. Okay, so that gives me log of 2x plus 1 equals negative 4. Yes? Okay, now what? Change forms, right? Okay, what's my base? 10 is my base. So this is 10 to the negative 4th power equals 2x plus 1. Can I do 10 to the negative 4th power? Yes. What is it?
0.0001.
So it's 1 over 10,000. Yes? Subtract 1. So if I subtract 10,000 over 10,000, right? Because that's 1. Okay? I get, give me some more space, negative 999 and 9, so negative 9,999 over 10,000 equals 2x. Divide by 2. Dividing by 2 is the same as multiplying by 1/2. So I get negative 9,999 over 20,000. If you were in decimal form for this one, that would have been negative 0.4999. Okay? Good times. Good times. Okay?